Hello. In this video, we're going to look at a new topic called Implicit Differentiation, 3.5 in your textbook. The motivation for this section is the following question. What's the derivative of y squared plus 3x squared equals sine x plus 4x? Well, if you look at it, we have a bit of a problem. Normally, all of our questions begin with the simple y equals. Or sometimes we have f of x equals. But in either case, on the left-hand side, we always have y equals or f of x equals. In this case, we have a very strange situation where the left-hand side is both y squared and 3x squared. There's no y equals. There's no equation or no function isolated to solve for, so how would you do the derivative? Well, we might, in this case we might be able to rewrite the equation in the form y equals fx. We might be able to get y all by itself. And so let's see if we can actually do that in this case. So we're going to move the 3x squared to the other side, giving us y squared equals sine x plus 4x minus 3x squared. Then we can go ahead and take the square root. So y is going to equal the square root of sine x, taking the positive square root, of course, plus 4x minus 3x squared. And then we can do the derivative. Y prime would be equal to, we'll use the chain rule, 1/2 sine x plus 4x minus 3x squared times, chain rule will give us cos x plus 4 minus 6x. Okay, so that didn't seem too difficult. If we have a situation where y isn't isolated, maybe we can just solve for y. But there's going to be situations where this actually isn't possible, where we have something so complicated that y can't be isolated. For example, what if we had something like this? What if we had maybe x cubed plus y cubed equals 5xy? Well, in this case, maybe you want to move the y to the one side. So you get y cubed minus 5xy equals negative x cubed. But now you say, wait a minute, I was trying to move the y's to one side. Now I've got an x on this side too. This term 5xy, if I put it on the right-hand side, then I don't have the y's together. If I put it on the left-hand side, I don't have the x's together. What in the world am I supposed to do? And so the answer, of course, is we need to use implicit differentiation. We need a new technique. So let's take a look at the method of implicit differentiation. So implicit differentiation. Step one is we're going to do the derivative right away. We're not going to do any solving, any algebra. Step one is going to be to differentiate both sides with respect to x. Step two is going to be to use the chain rule whenever differentiating a y. Anytime you see a y, we're going to use a chain rule, and I'll show you what that means. Step three is we're going to collect all terms involving dy dx on one side of the equation and all the other terms on the other side. And then step four is going to be to factor out dy dx and solve for it. Okay, I know that's a lot of steps, but let's go ahead and take a look at an example. Suppose we want to calculate this derivative. Hey, it looks like that question we were just trying to solve. How could we do it with implicit? Well, the first step is to do the derivative. So what is the derivative of x cubed? It's going to be simply 3x squared. What's the derivative, though, of y cubed? Well, if you think about it like, say, a trig function. If I was going to imagine sine of x cubed, the way I would do the derivative is I would use the power rule and get 3 sine x squared. And then I have to multiply, I know, by cos x, which is, of course, the derivative of sine x. But instead of writing cos x, I'm going to write derivative of sine x, just to show that I'm multiplying by the derivative of the inside, using the chain rule. Well, the same situation, the same technique applies here. We use the power rule, 3y squared. And then we multiply by the derivative of the inside, literally the derivative of y. Then we put equals, and we use the same method over here. We have 5xy Well, clearly there's a product and we have to use a product rule. So we'll bring the derivative of 5x is just 5, derivative of the first. Leave the second alone, plus, leave the first alone, derivative of y. Well, we literally write that as the derivative of y. It's kind of clever. We don't know what the derivative of y is, so we literally just write the derivative of y. Now, we're going to go ahead and move all the terms that have a dy dx to the left-hand side and everything else to the right-hand side. So notice here, this term and this term are going to go to the right-hand side because there's no dy dx with them. And this term here and this term here are going to go to the left-hand side. That's going to give us 3y squared dy dx minus 5x dy dx equals 5y minus 3x squared. Okay, so remember my goal here. I'm trying to solve for dy dx. I actually want to calculate dy dx. And what that means is on the left-hand side, I want to do a little factoring. Notice, each term here has a dy dx in common. So we can factor dy dx out of the left-hand side. Dy dx left with 3y squared minus 5x equals 5y minus 3x squared. Well, if I was doing a simple algebra problem, and you could imagine this as my x that I was trying to solve for, I would divide by the stuff that's multiplying the x, so the x would be all by itself. The same methodology applies here. I want to divide both sides by what's multiplying the dy dx. So I want to divide by 3y squared minus 5x, divide by 3y squared minus 5x, because that will cancel out this with this. Finally, I will have dy dx is equal to 5y minus 3x squared over 3y squared minus 5x. And if you notice, I've now solved my question. I have the derivative of y. Now, if you notice something about this implicit differentiation, we're using the word implicit. We need to be a little bit more precise with what I mean in terms of implicit and explicit. So I'll give you an example down here. An explicit function is a bit easier for you to understand because you're used to them. An explicit function looks like this. An explicit function. It's maybe y equals 3x squared minus sine x. It's explicit because you're literally explaining what y is. You're defining y. You're saying, hey, y is equal to this stuff. It's being explicit about what you're saying y is. But an implicit function is a function like x cubed plus y cubed equals 5xy, like the one we just did. Because you're not exactly saying what y is equal to. You're saying, well, x and y, both of them being cubed, are equal to 5xy. You have some type of relationship, some type of equation, maybe even some type of function if it passes the vertical line test, but you're not being explicit. You're not explicitly saying what y is equal to. So this is called an implicit function. The function y equals, maybe you could solve for it with enough work. It's implied that there is a y here, but it's not explicitly given. So it's time for a Plicker question. We're going to do our best to keep the Plicker questions alive through this course. And so here we have a nice multiple choice question. Which of the following is an implicit function? So I'll give you a couple minutes to think about this. Do your best. Pause the video. I don't expect you to hold up your Plicker card, but try to take a guess. Maybe write it down. Which one of these do you think is an implicit function? All right, so the correct answer is D. D is an implicit function, and let's go through why that's true. A is clearly explicit because it's y equals. B is also explicit because it's f of y equals sine of y. It's a bit weird there. It's a bit weird because you would expect there to be x's, but this is just a function with another variable. You're explicitly defining how the function works. Again, over here, it's a bit weird. Normally, you have y equals a bunch of stuff. Here, you have x equals a bunch of stuff. But again, this is an explicit function. It's just an explicit function of y instead of an explicit function of x. It's still explicit. But this one down here, notice how there's x's and y's on both sides, or sorry, on the same side of the equation. When you have x's and y's on the same side, you have an implicit function. So d is implicit. So in this example here, we're going to calculate the derivative and then use it to find the equation of the tangent line. So let's just focus on the first portion there. We're going to go ahead and find the derivative, dy dx, of this implicit function. Well, initially we have a product rule to look at. So let's do that first. Derivative of x is just 1, x plus 3y, plus x. Derivative of x is 1. Derivative of 3y is 3. Again, the constant factors out. Derivative of y, dy dx. Plus, if we have y squared, we have a power rule, so 2y. And then we have to multiply by dy dx because of the chain rule. Equals, careful here, the derivative of 11 is 0. Now we're going to go ahead and multiply everything out so we can eventually isolate for dy dx. This gives you x plus 3y plus x plus 3x dy dx plus 2y dy dx equals 0. We're going to go ahead and move everything with dy to the left-hand side. You're almost treating dy dx like a variable you're trying to solve for. And we'll move the other terms to the right-hand side. So we'll get 3x dy dx plus 2y dy dx equals negative 2x, just grouping the x's together, minus 3y. Now we factor out the dy dx because it's in common, giving you 3x plus 2y. And finally, you go ahead and divide it out. 3x plus 2y is divided out on both sides, giving you the nice formula for dy dx. dy dx equals negative 2x, subtract 3y, over 3x plus 2y. Now, our goal was to calculate dy dx, and we've done that. And the second part of the question asks us to find the equation of the tangent line. Well, to find a tangent line, we need two pieces of information. We need a point, and we need a slope. The point is given to us, and now we need to use something about the derivative to calculate the slope. Well, it's actually very interesting. We have the derivative of y, so we just need to plug in to find the slope. This, again, is our derivative, and the derivative gives us the slope of the tangent line. But what's interesting is this derivative is both x and y. There's both x and y in what you can think of as the equation or the formula for slope. The formula for slope needs an x and a y to be plugged in. Thank goodness we have both x and y in our coordinate point. So you write it like this. You write dy dx evaluated at the point 1, 2. So our point is 1, 2, and we draw the straight vertical line to represent that we're evaluating at 1, 2. It's like plugging it into a function, but we have to plug in both x and y. So you get negative 2 times 1 minus 3 times 2 over 3 times 1 plus 2 times 2. Doing a little bit of arithmetic gives us negative 2 subtract 6 over 3 plus 4, which gives us a final answer of negative 8 over 7. So therefore, our final answer would be y minus y1 equals m x minus x1. That is the equation of the tangent line. Let's go ahead and try a quick multiple choice question. Determine the derivative dy dx of this function. Looks like we're going to need a little bit of implicit there, and it looks like we're going to need to simplify. So I'll give you a chance, pause the video, and see if you can figure out the answer to this multiple choice question. So hopefully you've given it a try. I'll work out the solution here. You get negative 8x to the 7 plus 8y to the 7 dy dx equals 0. Move that negative 8x to the 7 to the other side, giving you 8y to the 7 dy dx equals 8x to the 7. Divide both sides by 8y to the 7, 8y to the 7. And the 8's cancel out, giving you your final answer of dy dx equals x to the 7 over y to the 7. So the correct answer here is A. A is the correct answer. Let's go ahead and try another derivative question where we have to use implicit and find the equation of the tangent line. So let's start off right away with our derivative. The derivative of x is 1. Derivative of sine is cosine. While we're doing the chain rule here, it looks like we have a product rule, x times y. So let's be careful here. Derivative of x is 1. So we'll have 1 times y plus x derivative of y is dy dx plus 3y squared dy dx equals, again, watch out for it, the derivative of 1 is just 0. So we'll isolate by first, of course, expanding. We can't move the dy dx's all around until we've expanded out this multiplication we have here. So we'll do that first. 1 plus cos xy times y plus cos xy times x dy dx plus 3y squared dy dx equals 0. So we'll keep the dy dx business on the left-hand side. That's a cos xy x dy dx plus 3y squared dy dx equals negative 1, subtract, I'm just going to put that y in front, y cos xy. Next up, we factor the dy dx. Again, I'm just going to put the x in front. It makes me feel more comfortable to have the letter in front of the trig function. So x cos xy plus 3y squared equals negative 1, subtract y cos xy. And finally, we have to divide it out, giving us dy dx equals negative 1, subtract y cos xy over x cos xy plus 3y squared. So this is the derivative of y, and we're going to use it to calculate the tangent line. So we were told the point was 0, 1. So we write dy dx evaluated at 0, 1. That'll be equal to negative 1, subtract 1 cos 0 times 1 over 0 cos 0 times 1 plus 3 times 1 squared. We do want to know our basic values of the unit circle. Cos of 0 is going to be 1, so that's helpful to know here. That'll give us negative 1, subtract 1. 0 times anything is just 0, and then 3 times 1 squared is 3. So we have our final dy dx as negative 2 over 3. Putting this together with our point gives us y minus y1 equals m x minus x1. And there we have our equation of the tangent line. So let's do another implicit example here, one that's a little bit more complicated, throwing in some secant and sine and whatnot. So we'll start on the left-hand side. Derivative of secant is going to be secant xy tan xy times, the chain rule tells us we have to do the derivative of x times y, and unfortunately that also means a product rule. 1 y, derivative of x is 1, plus x dy dx plus, well, we've definitely got a product rule going on over here too. So this is going to be cos x times y plus sine x dy dx equals, now be careful here, this looks like a product rule. And you could use unnecessary product rule on it, a concept we've mentioned briefly in class, but you really shouldn't, because this 7 is a constant, and you shouldn't think about this as x squared times 7. You should think about this as just 7x squared. When you're doing the derivative and there's a constant in front, you just rewrite the constant and then do the derivative as normal. So if the derivative of x squared is 2x, put the 7 in front, and you have 14x. No need to do a product rule. All right, let's start to expand things, see what we get. So here we're going to have, again, I feel comfortable writing the y in front rather than putting it with the trig functions. So I'm going to write y first as we expand. Secant xy tan xy plus, and we've got x dy dx with our secant xy tan xy plus y cos x plus sine x dy dx equals 14x. All right, we'll move the dy's to one side and everything else to the other. So here on the left-hand side, we're going to have x dy dx secant xy tan xy plus, well, we have another term with a dy dx. It's off screen, but it's sine x dy dx equals, and the other terms we're going to move to the right-hand side. So that's going to give us 14x minus y secant xy tan xy minus y cos x. For our last step, we're going to have to factor and divide out. So we're going to have here dy dx left with x secant xy tan xy plus sine x equals 14x minus y secant xy tan xy, and then still minus y cos x. For that final step, we divide it out, and so we would write underneath this divided by x secant xy tan xy plus sine x, and the same thing happens on the other side. So over here we're going to divide out by that monster denominator divided by x secant xy tan xy plus sine x. So our final answer, drum roll please, dy dx is equal to 14x minus y secant xy tan xy minus y cos x all over x secant xy tan xy plus sine x. So another question here, maybe involving some exponentials. Let's see if we can find dy dx in this case. So we're going to start with that left-hand side and do the derivative. E to the power of sine x times cos x with the chain rule, plus 5. Derivative of cos is minus sine e to the y. Then we need a chain rule. Derivative of e to the y is e to the y. And then there's one more step. We have to put dy dx. So 3 portions for that chain rule there. Close off that bracket. The derivative of e to the pi is 0 because e to the pi is a constant. Let's clean that up a little bit. We're going to have e to the sine x times cos x minus 5 sine e to the y dy dx equals 0. So we'll move that e to the sine x times cos x to the right-hand side. Minus 5 sine e to the y dy dx equals e to the sine x cos x, negative of course because we moved it to the other side. And then you divide both sides. In this case we didn't have to factor. It was just negative 5 sine e to the y times e to the y. Negative 5 sine e to the y. Giving you your final answer of dy dx equals negative e to the sine x times cos x over negative 5 sine e to the y. Time for a quick Plicker question here, multiple choice question. Determine the equation of the tangent line at pi by 2 and 1 to the equation y equals sine of x times y squared. So I'll give you a moment to think about that. So let's go ahead and find the tangent line by first finding the derivative. On the left-hand side we have dy dx, and on the right-hand side we have cos xy squared times, product rule gives us 1 times y squared plus x times 2y dy dx. Now, we technically have to isolate for dy dx, but if you wanted, we could plug in the values now. Eventually, we're going to have to plug in for x and y. And so, hypothetically, you could plug in for x and y at this point. You don't have to, and I would fully understand if you went through all the steps, but just to show you another method, I'm going to plug in x equals pi by 2 and y equals 1. So I'll have dy dx equals cos of pi by 2 times 1 times 1 times 1 squared plus pi by 2 times 2 times 1 times dy dx. Now we use some trigonometric rules, and we know that cos of pi by 2 is actually going to be 0. So we have 0 times 1 plus pi times dy dx. But of course 0 times anything is just 0, and that gives us dy dx equals 0. Well, that simplifies quite nicely, because now we get y minus y1 equals m, which is just 0, x minus x1, or y is equal to 1. So the correct answer is A. For homework, make sure you try the questions on page 215, 5 to 32, and 35 to 38. Please omit question 17. Thanks for watching.